So, hey guys, today is our day 15 of doing Leetcode daily until I get a job. So, let's start with the questions today. And we have graph. Yeah, we are left with these two questions. One is redundant connection, and second is the word ladder. So, let's start with the first question, which is redundant connection. Okay, so here what we need to do is that in this problem, a tree is a undirected graph that is connected and has no cycles. Okay, you're given a graph that started as a tree with a nodes labeled as 1 to n with one additional edge added. The added edge has two different vertices from 1 to n and was not an edge that already existed. Okay, the graph is represented as an array of edges of length n where edges I is a to b, means there is an edge between the nodes a and b in the graph. Return an edge that can be removed, so the resulting graph is a tree of n nodes. Tree is what? Undirected graph that has no cycles. Okay, it currently has a cycle, right? So we have to remove any one of the edge so that it becomes a tree. And which is the redundant connection which doesn't already existed. So here we can like see if we can remove any of the edge and it will be a tree. But it is given that there might be multiple answers, so we just have to return the last in the input. So that's fine. In this input, whatever is the last redundant possible, we have to remove. We have to return that. Okay. So what we can do here is that if we know about the union find algorithm, we can do this really easily. And how is that? Is because we can say um, yeah, these are the three nodes. Okay, 1, 2, and 3. Correct. Okay, if these are the three nodes, what we know about it is that in what union find basically does is union find algorithm. Okay, union find basically uses the method of finding the parent of one node and see if that connection is even needed or not. Okay, we will just union the two different graphs or different nodes and compare their parents basically. So like, see, how will we do this is that union find can be used in a different approaches, different type of questions solved using union find. But here how union find is used is that let's say if two nodes are there, okay, and they have the same parent, we know that parent of a is b, okay, and parent of c is also b. So if we know for sure that they have the same parent, that if there is any edge between them, we can just remove it, right? It doesn't make any sense, because if they have the same parent, a tree is what? There is a parent and there are child nodes. This is actually a tree, right? And there is no cycles in it. So we have to make a tree ultimately where there are childs, but there is no edge between the childs. Okay, between the childs there is no edge. Correct. So if it has a parent and it has another child, then these are the childs for this their parents. There is no edge between them also. So edge is always between the parent and a child in a tree. There's no edge between siblings in a tree. Okay, and if there is, that's a problem. Okay, so we are going to do that approach only, and you will now say that, let's just say, just a second. Now you might say that this is one node and this is one node. Can there be an edge between these two? No, still there cannot be an edge between these two, because we know that this its parent is this. We will find the last parent possible, okay? So that we have the best answer for both the nodes. We will find their lowest common ancestor. Okay, so for this node, this is its parent and its parent is this. After that, is there someone else whose child is this? No, this is the final boss actually, and its parent is this. So they have the same parent. So they cannot be joined here. Correct. So so that's how we can do this question, and let's like start implementing this in code. How we can do this? Okay. So firstly, write a function to find a parent. Okay. what we can do is that it will return int, correct? So int finding the parent, and we will just pass on the variable that whose parent we need to find. Okay, so if parent of this, we will make a vector, a global vector parent, and we will fill it. Just wait for some time. Like if the parent of this x is x itself, it is its own parent, like it's the root node, then we will return x. Else if this is not the parent of itself, then we will find the parent of x and we will return that, correct? So this recursion function will give us the parent of x. We don't have to worry about it in any way. Now number of edges we need to know. Number of edges is what? Edges dot size. That's actually the node, number of nodes. Okay, it is basically this. Yeah, obviously, like if there are like 5 edges, then there are 5 nodes. Okay, now we will make a parent vector. We will just make a parent vector we have made already globally. We will just resize it to n+1 and 0. Now we will set parent for each node. We will set parent for each node. Okay, and for int I0 to I less or equal to n I plus plus, we will do what is that parent of nodes are starting from 0 to n, right? 0 to n, 0 1 2 3 4 5, are they? 0 is not included, so we just don't have to worry about that actually. Okay, is it, we just have to worry about the nodes which are here. Okay, so if 0 is not there, it will not just be considered. That's fine. So parent of any node is currently itself. We will just consider that initially every node is a parent of itself. Okay, now if every node is a parent of itself, we know that, then um, then let's say our answer is we have to return a pair, correct? So and that's a vector actually. So vector int answer size to initially those values are 0. Okay, now we will start iterating this edges vector. What we will do is that for auto it of this edges vector, we can start iterating it. And while we are iterating it, we have to take these two nodes of this edge. We are at particular edge and we will take the two nodes of it. Like we are at 1 and 2 initially, we will take one node is 1, another node is 2. Okay, so int x is the parent of it0, and int y is the parent of 2, which is it1. So we will have to find it1. Okay, in this way we will find the parent of both of these nodes. Okay, if the parent of these nodes are not equal, if the parents of these nodes are not same, they are different nodes, their parents are not same, but still there is an edge between them, so one must be a parent of another, right? See, if there are these two nodes, let's say any of the two nodes here, and there is an edge between them, and they do not have a common uh, parent, their parents are different, let's say this, then we can set them as parent of each other, or we can set any one is parent of another. So we can set that parent of y is equal to x. Okay, we can say, you will understand why I'm doing this. Okay, and if they have the same parent, if x is equal to y and they have the same parent, then exactly that's our concern, that if they have like its parent is this, its parent is this, they both have the same parent, but still there is an edge between them, And how do we know there's edge between them? Because that's why we got this. That there was edge between them and we are just taking the two corners of the edge. If there's a edge between them, it is unnecessary edge. We can just remove it. Correct? So if their parents are same, that's how we know that we have to remove them. So res 0 will be it 0 and res, not actually res, it's answer 1 will be it1. So we can just okay, that's how we do it. And we just have to return the rest answer. Okay, so how will this work now is that initially 1 and 2 will come. Let's try it on this. 1 and 2 will come. So it0 is 1, it1 is 1. It1 is 1, it0 is 1, it1 is 2. Okay, so we'll find the parent of 1. Who is the parent of 1? Initially everybody is parent of itself, so x is also 1, y is also 2. So they are not equal, but there still is an edge between them. So if they are not equal, parent of 2 will we will make 1 as the parent of 2. Now 1 3 comes here. Their parents are also different. 1 is a parent of itself yet, and 3 is also a parent of itself. So 3 we will change the parent of 3 as 1. So 2's parent is 1, 3's parent is 1. They both have the same parent, but next edge is 2 to 3. So that means that they have the both parents same, like 2's parent will be returned 1, 3's parent will be returned 1. Both are same. If they both are same, there is no need of edge between them, 2 and 3. So we'll just store this in the answer and we'll return it. Yeah, this is what we have returned, 2 3. So that's how this is done. And yeah, that was pretty easy. So let's try and running it and see if we are correct. Yeah, it's correct. And we try submitting it. It worked. Next is the word ladder, a transformation sequence from word begin word to end word using a dictionary word list. There's a sequence of word that is begin word to s1 to s2 to sk. Okay, every adjacent pair of words in this sequence differ by only single letter, and every si in this word list, note that begin word does not need to be in the word list. Sk is the end word, so end word needs to be in the word list, right? Given two words begin with end word and dictionary word list, return a number of words in the sorted transformation sequence from begin word to end word, or 0 if no such sequence exists. So basically what we need to do is that we are given a begin word, we are given a end word. We have to reach from this begin word to end word through some kind of sequence by jumping from word to word. And let's say this is the first word, this is the second word. Similarly, we have to reach here. Okay, so how do we find the next word is that if b is something, a word 1, let's say, then s1 and b must differ in only one letter, and all of the rest of the letters must be same. Like if b is dog, like begin word is dog, then the next word can be anything which differs in only one letter. Like it can be cog, it can be for, like it only differs in one letter. It can be top. Okay, one letter must be different. Apart from that, everything must be same. So, and we are given a dictionary here, word list. We can take, we have to take these words, these intermediate words from this word list, and this and also be like whatever we change the word into, it must be in the word list. So end word must be in the word list. So this begin word doesn't necessarily need to be from the word list itself. It is a individual word, it's a separate word, doesn't necessarily need to be in the word list. But rest of all others, like whatever we change the word into, it must be from this word list. Okay, so how we can approach this is that we can use bfs for this. See why the bfs is better in this case than dfs. There it has a proper reason that why BFS is better in this case is that what BFS does is BFS go to a particular level and explore it whole. Then it go to next level to explore. Okay, but DFS, what DFS does is that it go to the depth of one way. When it hits a dead end or the solution, it will backtrack and will explore the other way. Like it will go deeper into one way, but BFS will explore one level of the all the solutions possible, then we'll go to the next level. Okay, that's what we need right now, because on the just the next step we just need the word with one letter change, so it will try to change every letter of the word, and we'll see that if that next word exists. Like if we have the dog, okay, we will do what is that we will change this letter to everything else which is possible. Like instead of D we will write A, B, C, E, F, G, H, everything, and we will see that after replacing this word is that new word present in the word list. If it is, then we'll go to the next letter, next word. Okay, so that's how we do it, that we will explore the one level of the solution and then we'll go to the next level. That's why BFS is much more beneficial in this question to us as compared to DFS. Okay, so we will apply BFS and how BFS is and one more thing is that we have to return the sequence length, return the number of words. Okay, we have to return the sequence length of it, that which is our solution. So we have to keep track of on which sequence number we are currently. So for that reason only, we will take a queue of pair, and the pair will be string and int. String will be the word itself and int is its position in the sequence. Okay, so we will take a queue, and in this queue we can just directly push what, the begin word. We have the initial word already, so we will just do this begin word, and its position in the sequence is first, correct? And after that what we can do is that we can have a set to store this word list, because we have a vector of this word list and numbers can be repeating in here, and from a vector erasing the things might be a bit difficult. Because let's just say that we found a letter, we found a word which is just next to begin word in the middle of this word list. Now we need to remove it from the word list that we have already find it. We will not be repeating it again in the sequence, so we have to remove it from here. How will we remove the middle element from the vector? It will be much more complex than as compared to a set, because in the set we can just directly erase what we want. Okay, it will do it in log n time, because set firstly doesn't have one more benefit of using set is that set only stores the distinct words, distinct elements. The elements cannot be repeated inside a set. So we'll take an ordered set because we don't want ordering in it. Ordering will take extra time, so we'll take an ordered set, and it will be of string. Okay, and that will be s, and we will import whole word list into it. So how we can do this is word list dot begin to word list dot end, correct? Okay, yeah, we get the set now, we got the queue now. Now one thing, it is given that begin word does not need to be in the word list, but maybe it is in the word list. So if it is in the word list, we can just remove it. Okay, so we'll just s dot erase the begin word. If it is in the word list, it will be removed. If not, we are okay with it. So the next will be, we'll start the queue now. While the queue is not empty, we will run this loop, and what we will do is, let's firstly take the word in the queue in the front of the queue. So queue dot front dot first will give us the word, and string int count will give us the number of words we have already found in the sequence. That is, int count will be that we have found only one word up to now, so it is 1. That's why its position as well as the count. So that's the same thing. So we can just do q dot front dot second. Fine. Now we will remove these elements, remove the current element from the queue, and we'll just q dot pop this element. Take it. So if the current word which we just found in the queue, it is the end word. So that, what does that mean? That begin word is the end word. If they both are the same, we will just return 1, right? One sequence of length is 1. They're both the same. So if word is the end word, we will just return the count. And why is it necessary for further steps also, we'll just see. Now we will just try all the possible transformations for this current word. Okay, we will try to change every letter of this word and see if it exists in the word list. Then we will go further with it. We can push it in the queue that this is the next word. Then we will take its word, take its position, and if it is the end word, we will just return the position. Else we will go further with it and we will try to change all the letters in it, and we will see that if after changing the letter, the word which is formed, is it in the word list. If it is in the word list, then we will go forward with that word now. So yeah, we can do this, that int I is equal to, start from there, correct? Yeah. But before that, yeah, we can start. It will, oh sorry, it will not be int, it will be char e to I less than or equal to z, correct? And we will go to each of the character from a to z. Let's just store the current okay, we will just store the current letter which we are changing also. We will have to store it. Okay, we have to store it. How we can store it is that char original, what we have currently, let's just store it because we will need it later. Now we can change it. We have to store first, like if in the dog we are changing d, let's first store the d. Okay, because later we need to replace it again. So it will be word I is what we are changing. See, okay, this is the inner loop. Basically we have to form an outer loop also. So int I 0 to I less than word dot size I plus plus. Okay, we have to try changing each letter of the word. So we will iterate through the whole letter, so all the word, and at each letter we will try to change that letter into all of the possible characters. That's 26. So its complexity will be n, the size l, the size of the word. 26 is the inner loop and n is the outer loop, the length of this begin word to end word. Okay, so n into l into 26 is the complexity of this, and words length can be, yeah, length can be 10 at max. So if the length is 10, then it will be 10 into 26, the maximum complexity, 10 into 26 into the length of this, the difference between the end word and begin word. That's what we have. Okay, so what we gonna do is we will start this and we will move this for loop inside this. Okay, fine. We will just change this character to C because I we have already took in the outer loop, so we will take C. And word I, let's just shift it up for here. Fine. Okay, we have the original character now. Now we can try changing this character, that let's say word I is C. Okay, but where we are currently. Now we have to check if the set has that word. Does it has that word? And it will be like this. This condition will return true if it has the word. Okay, if it find the word before the end, we have the word, means that doesn't mean So we will just remove that word from the set and we will push it into the queue. So we will push it into the queue, and how we are gonna do that is this plus count plus one, count plus one. This is the next step. Okay, and after going out from this loop, we will just reassign it its reassign the word its original character. That take your original character back. We have done our job. Okay, so ultimately if the end word is found while running this loop, we will just return the count, and if the it cannot be found and the loop ends, the end word is nowhere to be found, then we will just return 0. Fine. Yeah, it should be fine. Okay, word. Okay, we forgot the semicolon. Fine. Let's try submitting it. Yeah, it's 26 minutes already, and yeah, we are good with it. So these were the two questions for today. The video will be small today, shorter today as compared to previous days, but we'll start a very important topic from tomorrow, that will be the DP. See, what we are going to do here is, what we are trying to achieve here is the consistency. Okay, the daily we are doing something, and now if we see that we have completed the at least these questions. Okay, if not everything, at least we are doing these questions, and we are exploring each of the topics and doing some of its questions. So we have done the array hashing, we have done the two pointers, we have done the stack, binary search, sliding window. These 5 topics we did. Then we did the trees and the graphs. Okay. Now next we will be doing 1D DP. Okay, and then we'll be doing 2D DP. So if we check out 1D DP, this is this. So through that process of doing this, these lists is the purpose is that we can at least have our basics clear. At least we have some approaches that we know that how to solve this question, and we have our hand over these questions, that if we got an interview in any company, we are just not just blank, we can think of something and we can solve the questions. Okay, after completing this list, we will go into the detail of each and every element, each and every topic, and we will do a lot of questions regarding that. Okay, we won't stop doing the lead code, so we will be doing a lot of questions from all the topics. It's just start. Okay, it's just we are just making ourselves up, and we are just motivating ourselves, and like improving our consistency of doing things daily at a speed. Like regularly, if we're doing 2 3 4 questions, sometimes we do 5 6 questions, we are doing something every day. Okay, and that's why we can see that we have a consistency here. We can see our streak. Okay, that I just formed this account solely for this purpose only, and we have done 60 questions, and we like didn't realize that we have already done 60 questions, and we have a streak of 15 days. We are doing questions consistently from 15 days. Today is our day 15, obviously, as we know. Okay, so yeah, we're going good. Next we'll be doing DP, and okay, that's nice. And we will start tomorrow with the DP, and that's all for today, guys. Thanks. We'll meet tomorrow again. Bye.